Hello everybody. In this video we are going to talk about timers in Arduino and in general. So one of the very important things and tasks that you need to do in mechatronics in general is to use timers and do something based on a passage of time. So it is really important to know how to do something at a very specific time or after so many seconds or milliseconds or stuff like that. So the timer that we have in Arduino in general is a counter, okay? So it is using the Arduino's clock, and it counts every tick of that clock, every pulse of that clock, it counts one up. And so if you can basically scale it properly down, so you can basically get the specific times corresponding to seconds, milliseconds, microseconds, and so on from that. So as I said, most of the time you need to slow that clock down because for Arduino, that clock is about 16 megahertz or 16 million ticks or cycles per second. So if you want 1 millisecond, you have to slow this down quite a bit before you can use it. And that scaling is typically called a prescaler. So what you do is you send the clock from the Arduino, and then you can use different scalars, which is basically a power of 2. So that is similar to constantly dividing by 2. So sometimes you might, like in this case, you see it's like 2 to the 7, right? And 2 to the 7 is basically 128, correct? So if you use a prescaler of 128, that is like dividing that speed of 16 megahertz, dividing it by 128. So now your frequency is smaller, still quite a bit higher than 1 millisecond. So I'll show you if you want to get 1 millisecond, what is it that you exactly need to do. But basically, we are going to slow down the clock a little bit. Now, this counter keeps counting, and your counter has so many bits. The register for your counter has so many bits. So once it reaches the end of those bits and it counts and reaches the end of the numbers it can count, then it goes back to 0 and we say it overflows, okay? For instance, one of the timers that you have in Arduino is called timer 0. The timer 0 is only an 8-bit register. So the numbers it can count is anywhere from 0 to 255. And 0 to 255 can be counted very fast if you're using the clock. Okay, if you're going at 16 million counts per second, of course, it is not gonna take too long. Even timer number 1, which is the largest one, and it has 2 bytes or 16 bits, and it can count from 0 to 65,000. If you look at that, this 65,000 counts over 16 million or 16 megahertz, all it takes is about 4 milliseconds. So in 4 milliseconds, you already counted any number from 0 to 65,000 something, right? Which is 536. And guess what? Once it reaches this number, again, it goes back to 0. Okay, so that is where we say it overflowed. So that is the meaning of overflow. That is the meaning of prescaler, is to scale it down. Now, here, if I use a prescaler or of 64, which is 6 of those 2's back-to-back dividing, now your actual clock is like 250,000 hertz. And so if you use timer number 1 and count 65,000, so divided by that number, now it's about 262 milliseconds. You see, so going from this number to this number, right, which both of them are overflow of timer 1, the scale is what is this 64, is this prescaler. So you made your overflow to happen in 64 times more milliseconds. Instead of 4 milliseconds, now it overflows in 262, which is more useful for timing actual physical events, because 4 milliseconds is super fast. Before you know it, it's over. If you want to do any mechatronics task with it, 4 milliseconds is very fast. Most of your physical systems are not that fast, so you need to slow down, as I said. Now, What kind of prescalers are available and how many bits should you count for different timers in Arduino before you overflow? That is what you can see in this table. The regular Arduino Uno boards, they have 3 timers: timer 0, timer 1, timer 2. While timer 0 and 2 are 6 bits, timer 1 is 16 bits. 8 bits, sorry, those are 8 bits. This is 16 bits. So they can count a lot less than timer 1 can count. Now, what about the prescalers, the scaling down factor? So timer 0 has 5 prescalers, 1, which is like nothing, 8, 64, 256, and 10, 2 to the 10, 1024. And then timer 1 has similar prescalers, but timer 2 has a little bit more. So it has 32, it has 128 that these other ones don't have. Okay, so you see the difference between them. Some of them have more bits, so it takes them more time to overflow. Some of them have more, basically, prescaler factors. Okay, and what are their applications? So timer 0 is the default timer in Arduino. The functions millis and micros, I told you about the millis, but we're going to see more of that today. So these 2 essential functions are using this built-in timer 0. But it can also be used for pulse width modulations on pins 5 and 6. So pay attention that if you want to send signal out, pulses, anything, with timer 0, you should only apply it to pins 5 and 6 on the Arduino. On the other hand, timer 1 signal only goes to pins 9 and 10 if it's in the form of PWM. And since it can count more, then you can use it for precise timing, and for servo control libraries, you typically use timer number 1. And timer number 2, it goes to pins 3 and 11, and you can use it for custom timing and for audio processing and audio, working with audio signals. Okay, so the most powerful one, I would say, is timer 1. Timer 0 is like your default, and timer 2 is an extra one that you have, so you have 3 separate ones. Now, I'll show you when you work with timer 0, you have to be a little bit careful since it's the default and it's used in milli and micro. If you use it in 2 different versions, they will kind of overwrite each other and they will have conflict with each other. So I'll talk about that. But millis and micros, as I said, are 2 major functions. One of them returns the time passed in milliseconds. The other one returns the time passed in microseconds. Okay. Now let's see, how does this function milli even work? Because I want exactly this function to return to me something, some value right after 1 millisecond. How does that work with 16 megahertz clock? And how does that work with the fact that that function is using timer 0, so it only goes from 0 to 255, 8 bits? So how do we do it? We're going to use timer 0 with a 64 prescaler. So first we slow down the clock by 64. And then, as you can see, this is the hertz. If you divide the number by the hertz, you get the period of the signal. The period is 4 microseconds. So you see that every time this timer 0 counts 1 up, the time it takes is 4 microseconds. So if I can multiply this by 250, that is going to be 1,000 microseconds or 1 millisecond. Right? So if I can somehow count 250 counts of timer 0 at prescaler 64, that is the exact time that I want. The problem is this guy will overflow when it reaches 255, not 250. If it would overflow at 255, that would be perfect, but this doesn't. It only overflows at 255. Okay, so let's go with 255. If we go with 255, since you also count from 0 to 255, you have to really multiply by 256. So if you multiply that by 4 microseconds, you see you have an extra 24 microseconds compared to 1 millisecond that you have to kind of get rid of. So if you just let timer 0 overflow with prescaler of 64, the time is a little bit over 1 millisecond, 24 microseconds extra. How can I get rid of that? Is there any way to get rid of that? Now, this is what you do. So, once you do it, the way that you can do it is you let it overflow 64 times, and every 64 times is overflowing, then you're gonna skip one overflow. Okay, so you let it overflow for 64 times. The 65th time, you don't count that. So what happens? What happens is 64 overflows, each time 24 extra microseconds. That means 1536 for 36 microseconds extra. Now, since you don't count one of the overflows, remember, one overflow means 1024 microseconds based on what we just learned. So you have to subtract that 1536 from 1024. That is the remaining that you still should divide between all of those 64 of them, and that is 8. So you see the actual time that now it gives you is about 1.008 milliseconds. Okay, so it's quite a bit better. Compared to 1.024, now it's 1.008. You reduced it by a factor of 3. And that gave you a better timing. So the timing that the function millis will give you is not perfectly 1000 microseconds. It's a little bit extra. And it's the closest that it can be to it. Okay, so let's talk about timer 0 a little bit more. Okay, so we said we use it for millis, micros, pins 5 and 6 for PWM. But how do you set up the values or the registers for this timer? There are 3 registers for timer 0. One is called TCCR0A. Then we have TCCR0B, and we have TIMSK0. Now, TCCR stands for what? It stands for Timer Counter Control Register. Okay, so Timer Counter Control Register. This is for TCCR. Now, what is the difference between A and B? I'll tell you. And what is TIMSK? That is Timer Interrupt Mask Register. Okay, so just first of all, I want you to know what each one of them means. And the 0 in each one of them means they belong to timer 0. Okay? So now, what is the role of each one of these 3 registers? Let's talk about that part. The 0A, the first one, controls the mode. So you can use this timer in normal mode, in PWM mode. Okay, so these are the normal modes, basically. The PWM mode, and there is another mode called CTC. What is that? It means clear timer on compare match. Clear timer on compare match. What is it? I'll explain. But there are 3 modes that you can run your timer 0. Most of the time we use it in the normal mode, but you can use it in other modes too. Okay? And again, I'll tell you what CTC is. But the first thing is you can define TCCR0A to determine the mode. Now, how do you determine the mode? Here, you can see one example. It says you set it equal to 0. When you set it equal to 0, that means normal mode. Here is the structure for this register. You can see it has 8 bits. Bits 0 and 1, which are called WGM00 and 01. WGM stands for waveform generation mode. These 2 bits are the ones that determine the mode. The first 2. These first 2 are the ones that determine the mode, okay? And then the next 2 bits are not used, they are unused. The next 2 bits are for controlling PWM output on pin B, and the next 2, which are A, these are the controls for PWM output A. Okay, so there are 8 bits, 2 of them are not used. The first 2 are to determine the mode, and the other ones to control the behavior of the output pin. Now first, let's focus on this portion here. These first 2 bits that determine the mode. How do we know what number corresponds to what? Because you see here, 0 means normal mode. Well, if I want to go in CTC mode or PWM mode, what number should I assign for these 2 bits? So, or TCCR in general, so I can set it in any of those modes. So this is the table for it here. And as you can see, these 2, you can see that if they are both 0, it is normal mode. Now, if they are both 0, you don't need to individually set them to 0. Just by saying that the whole thing is equal to 0, that means these 2 are 0. Now, if the first one is 1, the second one is 0, you are in PWM phase correct mode. If it's 1, 0, then it's CTC mode. If they are both 1, then it's fast PWM mode. And then there are 4 other ones where there is a pin in TCCRB, not in A anymore. There is one of these bits that is in TCCRB in the second register, in this guy. There is one extra bit in that, and by setting that bit, it helps with these 3 others to go for these 4 other extra modes, which is a reverse mode that is not used, for a PWM phase correct, for a reverse, and a fast PWM, another, again, fast PWM mode. So these 4 we set if we use the extra bit in TCCR0B. Most of the time we only go with these 4 modes. If we don't want to go in TCCRB, we just use TCCRA. So now, let's say for instance, I want to use CTC mode, right? For CTC mode, I have to set the first pin, the WGM00 to 0 and the 01 to 1. How do I do that? Okay, here is an example. Look, it says TCCRA is WGM00, this symbol, and 1. What is that symbol? Have you seen that symbol anywhere? You might say, well, yeah, I guess that's a bit operation, right? What bit operation? You are right. It's a left shift bit operator. Okay? So basically this operation is, because you're not setting an entire variable. Remember, this is not a variable, this WGM00. That's not a variable. That's a single bit. So in order to set it equal to 0, you cannot just say WGM00 equals 0 or 1 or anything. That's a bit. In order to set it to a bit, use the bit left shift operator, and now this is kind of similar to saying that bit equals 0, and this is kind of similar to saying that that com is 1 or something. Okay? So this left shift operator is the one that you need to have. Now look at here. That is one scenario. What scenario is that? Look at that. That says put 1 into WGM00, so it makes this 1, and then the bit for what? The bit for the COM0A, that also is equal to 1. What is that bit? That's this guy. Correct? COM what? 0A1. That is this bit here. So it says this one to 1, and it says this one to 1. Okay, so if you want to turn any of these bits to 0, use a left shift operator, bit shift operator with the 1, whatever that you want. So let's say WGM01. That means setting it to 1. And if you want to bring another one and set that one also to 1, use the OR operation. So you say OR, let's say for instance I want this guy. Com what? Com 0 be 0. This is also what? It is by a left shift bit operator, set that also equal to 1. Okay, so like this. So as many as you want, just go ahead and use the OR and the left bit shift operator and set all of those to 1, and that will determine the behavior of your system. So as I said, for instance, if I want the CTC mode, all I need is to set my WGM01 to 1. That's all I need, and this is exactly this guy. Look, if I set that to 1, that means you are in CTC mode, because the other one by default is 0. So I'm only changing this one to 1, and that means what? That means I'm in CTC mode, as I said. So this is setting up the bits for TCCR0A, setting the mode operation for timer 0. Now, what is the second register, TCCR0B? That guy is to control the prescaler. Remember those numbers, 64, 128? How do you set those numbers? By setting the bits of TCCRB. TCCRB, similar to A, is 8 bits. So how do you set each one of the bits so you get those different prescalers? This is the structure for this guy now. Look. So this one really has these first 3 bits, and these first 3 bits determine the prescaler. So if you look at them, these first 3 are the prescaler setting of it. So if all 3 of them are 0, then there is no clock at all. You are not even using it. If you use the first one 1, the other 2 0, then there is no prescaling. But if you want a 64, then you have to have the first one and the second one to 1. If you want 1024, then the third one and the first one are equal to 1. So for instance, if I want to command it to use 1024 prescaler, what should I say? You're right. I say go ahead and use CS02, correct? Yes? Go ahead and use a left shift bit for that to 1. Or, again, that or means basically like an AND, because it's between the bits, so it is doing both of them. And then 1, and again what? This time use the CS00. So set both of them to 1. That means your prescaler is what? 1024, okay? And here you can see one example. Let me show you an example here for B. Here, look. You see it says the 00 is 1 and the 01 is also 1. And if you go and look at that table, you see that when the first one and the second one, they are both 1, the third one is 0, your prescaler is what? 64. So that comment here which says 64, you see that it's completely correct. So that is setting the prescaler, setting the mode. The third one is whether you activate the interrupt or you don't activate the interrupt. And when you activate the interrupt, do you go with overflow mode or do you go with compare mode, which is the CTC one? So this is the part that I need to explain. CTC and overflow I already explained to you, and to basically enable the interrupt. Now, what is the interrupt? That's my second video. But basically, interrupt is something that you use in your code to temporarily hold down on all other operations and give some operation the highest priority, and basically say, hey, whatever everybody is doing, hold on. First, this operation has to go and be executed. Then if you have extra time, I'll let the rest of you do your job. But interrupt is basically a way of giving priorities in executions in any code, including the C++ in Arduino. So here, if you look at this, and again, in a separate video, my next video, I explain it. So this timer interrupt mask register 0, which is this 0, you see all of these, by the way, you see they all have 0. That means they all belong to timer 0. So here you say this TOIE 0 is 1. When you say that is 1, that means you enable overflow interrupt. Okay, so what does that mean? The overflow is clear, means let this guy count all the way to what? From 0 to 255. Let it overflow, let it count to the max it can count. And when it reaches to the end and wants to go back, go ahead and activate an interrupt for timer 0, and inside that interrupt and inside the function for it, which is called the interrupt service routine ISR, in that ISR or interrupt service routine, you can do any operation that you want. Okay, so here we are enabling overflow interrupt for timer number 0 by setting the bit TOIE0 to 1. So first of all, what's the structure of this TIMSK0? Let's look at that. And we are going to come back and look at the rest of it. So if we go back and look at that TIM thing, right? So let's see, here we go. That is for timers TIMSK0. Look at that, look at the structure of it. So there are 3 major bits, TOIE0, OCIE0A, and OCIE0B. The first one, okay, if you set that first one, bit 0 of it, if you set that equal to 1, you're enabling overflow. If it's 0, then overflow interrupt is not enabled, it's disabled. Now, when you run it in CTC mode, what is CTC? I'll tell you in a second. When you want to do CTC or compare mode, then you can do it with basically match A, or you can do it with match B. You can compare your counter to 2 separate variables, and with those you can get 2 separate basically interrupts. So one time when this variable, the counter for your TCT mode in timer 0, when that is equal to this variable, and this is just a number that you said, like 200, 100, and the other one is when the counter reaches the other number, OCR0B, and again, this could be any other number. So as I said, this is time to talk about the TCT mode. What is TCT mode? Remember I said that when you want to activate an interrupt, what do you need? You need your counter for that timer to go to this maximum value, and when it reaches that and wants to restart back to 0, that is when your timer, your interrupt can go on, right? Can be enabled and be activated. Now, sometimes you don't want to go all the way to 255. You just want to go from 0 to, let's say, 100. And when you reach 100, you want to reset it back and activate this ISR, right? Why would you do that? First of all, because you want to count less. And by counting less or by counting more, of course, you cannot count more than the overflow number or max number. But by counting less, you are changing the time, correct? You are changing the time, because if you look back and look at these calculations that we have done, look here. So the time, you see that the millis was using, it was that 4 microseconds times 256. Yep. Now, if I could stop it at exactly 250, say, hey, don't go all the way to 255, just stop at 250, or in this case, go from 0 to 249 and stop, then that time will exactly be 1000 microseconds or 1 millisecond. And you might say, why don't you do that? Why do you count every 64 overflow and then skip one? Because this TCT mode is a little bit taxing on the calculations and it slows down the system. Okay, so you can do that if you want. If you want, you can just use timer 0 with prescaler 64 and do a compare mode. And when you reach 249, go ahead and what? go ahead and activate the interrupt to give you a time, and that time is exactly 1,000 microseconds or 1 millisecond. You can do that. So that is basically this number here, this OCR 0A or 0B. There are two of them that you can activate. So you can activate the ISR one time for, let's say, 100, one time for 200, or one time for 50, one time for 220. So there are two set values that you can determine for the maximum number it counts to and resets and activate ISR. And that is called the compare mode. Okay, the compare mode, or CTC, which we talked about. CTC means clear the timer on compare match. And clear means what? Means go back from whatever the number is, go back to 0, clean it up, and start again, start over. So in CTC mode, you don't count all the way to the max. You count to the max that you determine, not the one that is determined by the number of bits. Okay, hopefully I didn't confuse you further and I could explain what is CTC mode. Now, if you say, what are these variables? TOIE, OCIE, TCNT, OCR. What are these variables, right? Because there are lots of these kind of variables in timers in Arduino. What's the meaning of them, right? It's hard to memorize them. I mean, here you see that TCCR means timer control, timer counter control register. TIM-SK means timer interrupt mask register. What about these other variables, right? I see lots of new names here appearing back to back, and I have no idea what these stand for. So here I made you another table at the end of this presentation, and I tried to at least give you some of those names. So if you see TCNT, that's your timer counter register. So that's the what? That's the timer or counter for that specific one. So these two are what? These are the counters for timer 0. This is the one that counts all the way from 0 to 255 in normal mode, or 0 to this OCR number in CTC mode. Okay, that's your counter, timer, counter. Now, can you do anything with that variable other than it just goes up from 0 to whatever max number? Could you manually overwrite that number? Yes, you can. For instance, if you want to reset your timer manually, you can say, hey, timer 0, I want to reset your counter manually back to 0 somewhere, anywhere. You just say TCNT equals 0, and there we go. You reset it even in the middle of counting. Now, those numbers, that 100, 200, those numbers that you want to set instead of the max value, those numbers, OCR, what does OCR mean? OCR means output compare register. Now it could be for register A or for register B. So if you say 128, means, hey, only count from 0 to 128. Once you reach there, reset your timer. Okay, so I told you TCNT and OCR. I told you the TIM-SK also. I told you the, let's see, what else I need to tell you? The OCIE. So do I have OCIE? Let's see. And I looked at my table, and it's interesting that still I don't have these because there are too many of them. But if you want to know what that means, TOIE means basically so that I is interrupt, that E is enable, that O is the overflow, and that T is timer. So it is basically, and let me type it, I guess it's much better than my handwriting. So it is timer overflow interrupt enable. Okay, so that is the variable that when you set it, it is going to enable using overflow, and we just said that. Now, what is OCIE? This second one and the third one. So these two stand for what? O is output. So let me use another one here. So O is the output, C is compare, I is interrupt again, and E is enable. Okay, so this is output compare, and then what? Interrupt, enable. So these are these two guys. Okay, so now hopefully you have a little bit better idea of what each one of these guys mean, and what is their functionality. So if we move on, one other thing I want to talk about before I go to timer 1 and 2 and so on. Remember I said that when I was talking about the TCCR0, I said that the first 2 bits of that determine the modes of operation. So you see this WGM00 and 01, but there is another one called WGM02, and that, when that one comes in, that determines this extra other 4 modes of operation for timer 0. The question is, where is that bit WGM02? Because that, if you look at the timer 1, it's not in timer 1. Like, look at the timer 1, there is no WGM02 in it. This guy is not in this list. Where is it? As I said, it's in the TCCR0B, and that is what you can see here. This is the structure for TCCR0B. The first 3 bits are prescaler. If you look at the 4th bit, this is the one that helps the other 2 WGMs to determine the mode of operation. It also has 2 extra bits that are not used. And finally, it has FOC 0A and 0B, and FOC means force output compare A, force output compare B, which are the modes that are only for non-PWMs. Okay, so TCCR-A with 1 bit of 0B determine the modes of operation. The rest of 0B determine the prescalers, and this one is the one that enables either running in CTC mode or running in what? In regular overflow mode. Okay, so I guess I explained timer 0 for you. Now timer 1 and 2 are very similar. I mean, if you look at timer 1, the difference is it's 16-bit. You can apply PWM of that only to pins 9 and 10. Similar to the 1, it has 2 TCCRs. The only difference is it has 1A and 1B. Remember, for the other one, it was 0A and 0B. If you look back and look here, you see that for timer 0, these guys were 0A and 0B. Now they are called 1A and 1B. And this guy was called Team SK0. Now, if you look at this one, this is called Team SK what? 1. So these numbers basically match your timer number. And very similar. Again, A is the mode selection, B is the prescaler, and this one is to enable the overflow or the compare. For instance, if I take TCCR1A is 0, that means work in normal mode, just regular overflow. If I say 1B is CS12 equal to 1. What is CS12? If you look at CS12, 1, and the 2 others by default 0, that means a prescaler are 256. And then I say puts the overflow interrupt mode in enabled, and that is what? TOIE. If you remember, TOIE, I just mentioned, stands for what? You are right. TOIE, timer overflow interrupt enable. So just activate that so I can use it. Okay, and similarly, you can go to timer 2. Again, you see for timer 2, there is R2A, R2B, and SK2 with very similar structure. So these timers are very similar in nature. Now, let's, for a second, look a little bit more into the compare mode or CTC mode. And then I'm going to show you one example here in presentation. The other example I want to show you is this toggling here that you can see. I have 3 LEDs here. Each one is blinking at a different frequency or a different time. And I did that with different timers that I have. And I want to show you my code for that so you see how to use it. And then discussing this important formula for toggling or blinking frequency that you can use. So what I want to say is, one more time, summarize what does exactly compare mode mean. Means each one of your timers has a counter that you show it with TCNTX, and this X is the number for that timer. So TCNT0 is for timer 0, TCNT1 is for timer 1, and so on. So this TCNT is each time like 0 becomes TCNT0 plus 1. Okay, each time you're increasing it by 1 per each pulse that you receive from the clock, divided of course by the prescaler. And if this number reaches that OCR XA or XB, for instance, if this becomes equal to what? To OCR0A, if that happens, what's going to happen after that? So most of the time, this timer is going to reset back to 0. Goes back to 0. Okay? And then some function called ISR, as I said, interrupt service routine, is going to be called, and that function can do some specific job. Okay, so that is the nature of comparing. Now, what kind of action can happen when this condition is true? When this if is true, right? When these two are equal, then what's going to happen? So let's look at what can happen. By the way, this is a double equal sign. As you know, this is a logical one, not an assignment one. So here, the first thing that can happen is you activate your interrupt function, okay, the ISR. So activate that. Good. That's the first thing that you can do. What else? If you are in PWM, then instead of just interrupting ISR, you can toggle or set a pin. Which pin? The pin that is attached to the PWM of that specific timer. For instance, if you remember when we talked about these, let's see here, you see that if you're using timer 0, then you can set or toggle what? Pins 5 or 6, not the other pins, only pins 5 and 6. And then for timer 1, it's another 2 pins. For timer 2, it's another 2 pins. So if you are using them, the timer 0 in PWM mode, you can toggle or set pin 5 or 6, or you can basically just activate the interrupt function for it. Or if it's in CTC mode, then you reset the counter, which is this one, as I said, and this allows for very, very accurate timing because you can set this number to any number, as I said, that you want. And that allows very accurate timing. As I said, instead of 1008 microseconds that you typically see in the millis function, correct? Remember this case, as I said, if you only count from 0 to 249, not to 255, you can get exactly 1000 microseconds. So this kind of set variable, this compare mode, that is, by the way, CTC, that compare mode is really great for accurate timing. One last thing before I go to these examples is, you see that I have 2 of these compare match registers. One is OCR 0 or 1 or 2, A, the other one is B. And for each one of them, I can use a separate number, of course, right? So between these two, which one has higher priority? Which one is going to go and activate the ISR first or reset the counter or anything. It's A. A has higher priority. That one is the one that goes first. And then it's B. So it's the secondary compare variable compared to the A one. Okay? So your main timing function in CTC and PWM is your A. If you want to set up something, set OCR 0A or 1A or 2A to something. If you need a secondary one, then go and use OCR XB. So it's your additional timing control with lower priority. By the way, what's the name of the interrupts that is being called when any of these two compared modes is activated? What's the name of that ISR? Here is the name of that ISR: timer X comp A vect or timer X comp B vect. These are what? These are the functions or the routines, interrupt routines, that are activated when the variable TCNT reaches OCRA or it reaches OCRB. So let's look at an example of that here. So here I'm going to use timer 0 in CTC mode, and I'm going to use two separate max values of 100 and 200 on A and B. And using those, I want to toggle two pins. And these pins can go to two LEDs, so turn them on and off, right? So look here. Remember the timer? So here I define my timer interrupt function, ISR timer 0 comp A vect. Inside this function, you write whatever you want to happen when your counter, remember that TCNT0, when that one reaches your first variable, which is OCR, in this case 0A, and in this case this number is 100. When this condition happens, whatever you want to happen physically or in pins or whatever, you're gonna put it there. What do you want to happen? And you see what's happening is you go to pin number 6 and digital write on that pin the digital read of pin 6, but with a not. What does that mean? It means toggling. It means, hey, read whatever it is. If it's high, for instance, what is the not of high? It's low. So write a low to it. So if it was high, write a low. And of course, if it was a low, guess what? Write a high. So you see, you're switching the voltage on that pin number 6, which is, remember, attached to timer 0, and you're toggling pin 6. Now, if this pin 6 is going to some LED, guess what happens to the LED? The LED is gonna go on and off, like you can see here in this picture, in this video here, right? You see here, look. So here I'm toggling these LEDs at different frequencies with different timings, and that is exactly what you can see. You can make them blink. So toggling can be done in Arduinos with this simple yet very effective command. Read that pin, knot it, and write it back to the pin. Okay, this is amazing. Now for the other part, for part B, that you want to compare value to 200, go ahead and use the other interrupt that I have. This is timer 0 comp B vector. In that, go ahead and toggle pin 5 instead of toggle pin 6. And remember, 5 and 6 are the ones for timer 0. Yes, so whenever that TCNT reaches 100, pin 6 is going to be toggled. Whenever it reaches what? It reaches 200, then pin 5 is going to be toggled. Okay, and of course, since 200 is twice as big as 100, that means the frequency of toggling in pin 5 is half of the frequency of toggling in pin 6. How much is that frequency? We can find it, correct? How can we find it? We go back here and look at these calculations. Well, first of all, it depends what prescaler you're using on pin 64. So let's say if I go back, let's see what prescaler is used here. So if you go and see, you see for TCCR0B, I'm turning on both pins 00 and 01 to 1. And remember, that was a prescaler 64. That means your clock speed is 16 million divided by 64. Yes? And then for scenario A, you're only counting from 0 to 100. So you're counting 101 numbers. So whatever you get here, that is going to be the timing that you have, correct? And for the other one, very similar thing, except you count to 200. So you go from 0 to 200, so multiply by 201. That is going to be your next frequency here. And they are kind of, one is like twice as much as, I mean, of course, this should be 202, not 201. But you see that one is about twice the frequency of the other one is. Okay, so I can, by controlling these numbers, I can exactly determine very accurately what frequency I want the toggling to happen. So now look, in the void setup, what am I doing? I'm setting pins 5 and 6 to output so I can toggle them. I'm saying WGM01 is 1. That means run in compare mode. The prescaler is set to 64. What are the variables to compare TC and T0? The numbers are 200 and 100. And you see in this case, it's backwards actually. A is 200, B is 100. So in this case, I need to go back and redo this, right? Because this is 200, this is 100. So this is going to be 201, this is going to be 101, right? This is for A, this is for B. And I do that. So I set my compare values. And then for the activation of interrupts, I say what? I say put both of OCIE 0A and 0B to what? To 1. Means activate both of the interrupts that work for the CTC mode. So make both of them active. So now both of these interrupts will be active and both of them will do their job. If you don't do, let's say this one, if you don't do that, what's going to happen? Then this interrupt, even if you write it, even if you have this function will never be executed. So you will never see the LED connected to pin 5 to toggle and blink. Okay, it's not going to happen. You have to activate that interrupt. Otherwise, regardless of what you wrote up here, nothing is going to happen. Now, two other interesting things which I'm going to discuss further when we go to the interrupts. One is you have to enable globally all of the interrupts with the psi function. What is that psi? We'll get to it. The other thing is, in the loop, I don't need to do anything. Really? No, because these timers, when you set them up, they start counting. And anytime they reach to these predefined values, those interrupts will happen and the toggling will happen. So for the interrupts to activate and to work, I don't need to put them in the loop. I have no need to put the interrupts in the loop. You see, that's the beautiful aspect of the interrupts, that they keep using the counters and the timers and they do their job in the background. Whenever they reach some condition, then something happens. You don't even need to put them in the loop and slow down your code. Okay? Now, if you want to have a very accurate toggling or blinking frequency for your LEDs, this is your formula. The toggle frequency is going to be your clock. That's 16 million in the case of Arduino Uno, divided by prescaler. This is to slow it down, so let's say 256. Divided by a 2. Why 2? Because one time you turn it on, one time you turn it back off, or backwards. One time you go off, then you go on. So you need to do 2 togglings in order to go back to whatever it was. So first you go on, you do 1 toggle, you go off, you do another toggle, you go on. So you see it takes 2 ticks or 2 clocks in order to have 1 period. That's why you have to divide by a 2. And then whatever your OCR is, let's say we are using the A1, whatever that number is, since you are counting from 0 to that number, you have to add that number by a 1 and put it in the denominator to get your exact toggling frequency. Okay, this is the beautiful part. Now here you might say, why did you here multiply? Why didn't you divide? You are right, because here I'm mixing stuff actually in this case. This guy here is actually in frequency. This is in hertz. This guy here is the number of data you count, the number of pulses in order to get your basically time. So if you want to get a frequency here, not time, because time and frequency are reciprocal of each other, I have to bring it in the denominator actually. If the number I want at the end is to be hertz. If the number I want to be time, then I have to take reciprocal of this number multiplied by 201. So you're right, really we should not mix it like this. We should bring that OCR plus 1 into the denominator and not to the numerator. It is totally right. So if you want to use a formula, I recommend use this one here. Okay, so let's move on. So if I want to say the 3 different strategies for basically doing some toggling or anything else, faster or slower, what are those different ways that you can make something happen faster or slower? What are the 3 settings that you have under your hand? One is use different timers. Timer 1 and timer 0, they have different number of bits. One has 8, one has 16. So timer 1 takes a lot more time for it to overflow than timer 0. 2, use different prescalers. The bigger the prescaler, the slower the counting becomes, or the slower the frequency, so it takes more time for it. Or use different bit sizes in CTC mode. Right? For one of them use 100, for another one use 200 or 50 or whatever number that you want. So by changing prescaler, by changing the timer, or by changing these OCR numbers, you can change your final time. One other interesting thing that I want to mention is, remember that whenever we are using CTC mode, compare mode, right? We are using those compared to variable A or compared to variable B, OCR XA or XB. Now the question is, whenever you want to compare your counter against some fixed number that you determine, should you always run your timer in CTC mode? The answer is no. So you might say, can I run in the normal mode instead of this and still compare to some number other than the maximum value, which is 2 to the n, and n the number of bits of that? Yes, you can. You can still run it in normal mode and compare your counter to some number of interest. Yes, you can do that. What is the difference between that scenario and the scenario that you run it in CTC mode? The difference is resetting the timer variable. Okay? So, in normal mode or PWM mode, your counter keeps increasing. It will be compared to these OCR values. But when it reaches these numbers, your timer will not go back to 0. It keeps going up to the max number. Then it will reset. You see, that's the difference. Look, if I go back to the scenario here, let me do a little bit clean up so you can see. So in CTC mode, what you're doing is you are allowing your counter to go up, up, up until it reaches this OCR number. When it does, you reset it back to 0 and you can activate interrupt or whatever you want. But if you run it in normal mode, guess what? This condition happens. This one will not happen. and it still keeps going up until it reaches that 255 or 65,000 something before it resets and before an interrupt can happen. So it's not really a great idea to use it, okay? Yes? So keep that in mind. Here are some other kind of variables or acronyms that are available in Arduino timers, and I just want to mention them to you just very briefly. One interesting one is ICR. This is one of the very interesting ones. It's called Input Capture Register. What is this? This one captures external events on a pin for timer 1 only. What does that mean? So remember that you have a counter like TCTN or something, 0, 1, and it keeps going up until it reaches some maximum number that you set, or it's determined by the number of bits. And when it happens, some interrupt function can be called and activated to do something. But sometimes you need to know the time for some specific event. So for instance, if something happens on a pin, and in this case for this guy that is pin 8, if something special happens on pin 8, for instance the value of it changes or goes up or anything, then you want to know at what time, at what counter this event happened. So you want to set your ICR1 to this variable. Right when something happens at pin 8, you want to capture the time of some event. That is ICR1. It's a very powerful one, okay? It captures the time for a specific event, okay? Very, very important. Okay, so I talked about TIM-SKX. So the TIF-RX, which is basically the timer interrupt flag register. It has several bits, so it's not just one bit, it's several bits. It's a register. And the important bits of it is the TOVX, the OCFX, A, B, and ICRX. And ICR is this one, this input capture register. And the OCFs, which OCF stands for output control flag, these are 1 bits in it. And they indicate when some timer interrupt occurs. So you see here it says if TIF R1 and OCF1 is 1, that means comparing to that OCCR1, right, 1A has happened, whatever that number was, 100, 200. When that happens, okay, then do something, correct? And then there are other ones. There is PCICR, which is Pin Change Interrupt Control Register. There is PCMSK. This is Pin Change Mask Register, right? So the top one enables the pin change interrupts. The bottom one, select which pins trigger a pin change interrupt. Then we have EIFR, External Interrupt Flag Register, which stores the flag for external interrupts, the mask registers, and so on and so forth. There are lots and lots of these, and I don't want to use your time on each and every one of them, but there are lots of these variables and lots of these names. You see, the more we go down, the more of these variables we can see and how to set up each and every one of them. So I'll try to extend this table and put more variables on it, but in general there are too many of them, and knowing exactly the memory structure of timers in Arduino and which bit does what, that is some big knowledge, okay? So you can have several just lectures talking about these registers and the bits of them and what you can do by changing each and every one of these bits. Before I show you my sample code here that is toggling these LEDs at different frequencies, the last topic I want to briefly mention is we can say the timers in Arduino in general are hardware timers and software timers. A hardware timer is the one that is a physical thing built into the microcontroller, and it runs independently from the program, right? Remember, timer 0, timer 1, timer 2. These are physical timers, and they do their work. They continuous counting as soon as you enable them, even when your CPU is doing other tasks. For instance, it's doing some calculations. It is turning some pins to high and low. It is controlling a servo. It is doing whatever you can imagine. The timer in the back of the scene, it is doing its job. Remember when I said that here in this example, you don't need to do anything in the loop. The timers are doing their job. But if you had here some code added, let's say writing something on the serial monitor, you had some serial print line and stuff like that, and then doing some digital writes and digital read and whatever that you want, servo write, servo read, whatever you want, these will run, and those timers will do their job too and activate their interrupts without regard to these other operations of the CPU. Okay, these are hardware interrupts, which you have 3 of them here. Good. Now, a software interrupt is the one that you just do in a software just based on the times that those hardware ones provide for you. Milli and micro functions, millis and micros, are kind of software timers, because as you just saw, millis is basically using timer 0 behind the scene to generate something about 1,000 microseconds. So these are basically what we call a software timer. They are simulating the counters, and they are using those hardwares in the back to count something. So if you want to compare hardware versus software, hardware ones run in the background, software ones, they have to be run in the main loop. The hardware timers are very, very accurate. The software ones, they are not as good. About the interrupt support, the hardware ones do automatically, they have their own interrupts that you can call and they do their jobs. Not millis and micros, they don't have anything like that. You have to write something for them in the main loop. And then do they block execution? No, these guys can. Are they affected by any other code? No, these guys do. Okay, especially if you have delays, they will be affected big time. And the most important one is, when would you use these hardware timers? When you want to do very accurate timing, interrupts and PWMs. But in other general timing tasks, scheduling and stuff that do not need to be as accurate as these, you can go with millis and micros. So this is my last and most important thing. When would you use millis and micros? When your timing is not super sensitive and doesn't need to be extremely accurate. If you want to do a job at very accurate rate, you have to use the hardware timers. You never use the software timers. Now, finally, this is my code. You see here, I'm using pins 6, 9, and 3 for timer 0, 1, and 2, respectively. And the frequencies of toggling for them is 4 hertz, a quarter hertz, and 1 hertz for the 3 LEDs that you can see. The green one is about a quarter hertz, the blue one is about 1 hertz, and the red one is about 4 hertz in the back. And you see, because I'm dealing with variables used in interrupts, I'm using volatile variables, as I mentioned. And these are the states of LEDs 3 and 9, which are timer 1 and 2. I'm using a previous millis 0. This is what I use for the function milli. And then this is that number I want to compare against for CTC mode, 125. So in the setup, you see first I put all of those LEDs as output. For timer 2, I'm running it in CTC mode. I'm setting all these 3 bits to 1 to make prescaler 1024. I'm using 156 here to get exactly 1 hertz, and then I available my compare match interrupt. So you see I'm using timer 2, but not in regular overflow, in compare overflow. For timer 1, which I need to go at a quarter hertz, again, I use the same large prescaler, but you see here my number is 31249. You see this number is exactly calculated based on this formula I just showed you. Based on, let me see, just had it somewhere here. Based on this formula, I exactly counted, because I know this one, I determined this one, I picked this one, I know exactly this one. So from here, I can exactly calculate my OCR. And that's exactly what you can see here done. Again, compare enable match mode, and then I use the psi to enable all global interrupts. Now for timer 0, pay attention, I'm not using timer 0 in any mode here. Instead of using timer 0 individually, I'm using the function millis that is using timer 0. So here I'm using 2 hardware interrupts for 2 of my LEDs, and for the third LED I'm using a software interrupt, a millis. So I get my time from the millis, and if my current millis minus the previous one, which initially I said at 0, is bigger than this interval 125, which corresponds to 4 hertz, if that's the case, first of all, I go to that pin number LED for pin 6 and I toggle it, and then I update my time. Yes, so you see here I'm doing a software interrupt in it. And what are my interrupt routine functions? If timer 2 is activated, what does it do? So here what it does is it has this counter variable in it, and this local counter variable, each time that timer number 2 reaches the value of it, which is 156, this counter is going to go up. And when this counter reaches 20, it's going to be reset, and the LED state is going to be toggled. So here you're doing what? You're doing LED or pin toggling, basically. Now, why didn't I exactly use, this one. Why didn't I exactly use a number here instead of this 156? Why didn't I use another number so I don't have to do this portion? Why should I keep counting this counter until it reaches to 20 before I do toggle? The reason is I want this to happen at 1 hertz. And since timer 2 only goes to 255, the smallest frequency I can get out of timer 2, the lowest frequency I can get out of timer 2, if I use the highest even prescaler, which is 1024, if I use that and I use my maximum number, which is 255, the slowest timer 2 can go is about 30 hertz. Okay, I can never get anywhere close to that hertz that I want, like 1 hertz or so. So I have to, or a little bit more than 30 hertz, I have to count a specific number of counters so I can reach to that 1 hertz. Okay. Now, this is for timer 2. Now for timer 1, I don't have any problem. For timer 1, I want it to exactly go to quarter hertz, but this timer can count a lot more than 255. So if I just set it to some kind of mid-range number like that with a big prescaler like 1024, guess what? I can exactly get it to be a quarter hertz. So you see here, if I want to go to slow actions or low hertz, timer 1 can give me that, but timer 2 can never do that. Timer 2 is too fast because the max it can count is 255. So if I want to use timer 2 for something slow, I have to use this technique and using counters, and every 20 times it overflows at that exact number instead of 255 at that number, then I go ahead and do the toggling. Okay, so you see why I'm doing it differently. And for timer 0, I'm here using a software interrupt with function millis to do that. So you see all sorts of different ways of using timers in Arduino. And again, this is what I have. You can see the green one is quarter hertz, blue one is 1, and the red one is 4 hertz. And I used a 330 ohm resistor between the anode and the pin of Arduino, and the cathodes are all grounded. Okay, so hopefully you see how I can use different timers. And I'm going to share this code for you under video descriptions. Feel free to download it, play with it, and learn from using different timers in Arduino. Thank you so much. I'll see you in the next lecture.